Hi everyone, I'm Cheng Zhi, a PhD student at the Chinese University of Hong Kong. It is my pleasure and also quite interesting to present our paper, Maximizing the Reduction Ability for Near Maximum Independent Site Computation in such a special form. This presentation contains 4 parts: the background, some existing algorithms, our approach, and some experimental results. Given an undirected graph, an independent site is a vertex site that contains no neighborhoods. In this graph, 5 red vertices form an independent site, and it is also a maximum independent site since we can't find one that contains more than 5 vertices. As a fundamental NP-hard problem, the MIS computation has many applications, such as answering K-hop reachability queries. However, it's too time-consuming to mine an MIS in large networks, and is usually unnecessary to find an exact solution. Therefore, it is reasonable to efficiently mine a near maximum one as well. In this paper, we aim to find a near maximum independent site as large as possible at very low time cost. Then, let's go through some existing algorithms. The existing techniques can be divided into 3 categories: clonalization, branch and bound, and greedy strategies. Most of the existing algorithms can be regarded as the combination of the above techniques. Kernelization means constructing a smaller kernel graph based on some reduction rules as long as the MIS on the original and the kernel graph is equivalent. When no reduction rules can be used, exact algorithms will use some techniques such as branch and bound to search the exact solution. On the contrary, inexact algorithms will apply greedy strategies to further reduce the graph size. This procedure is repeated until the graph is empty. Here are some traditional reduction rules. For example, the degree 1 reduction rule shows that a degree 1 vertex is a better choice than its neighbor. As for greedy strategies, we can see that including a vertex into the independent site leads to discarding all its neighbors. Therefore, a vertex that has more neighbors is less likely to be included in an MIS. Based on this point, 2 simple strategies are widely used in existing algorithms. Vertex deletion strategy means discarding one of the highest degree vertices. That is, discarding an arbitrary red vertex in this example. As for vertex addition strategy, it means adding a lowest degree vertex into the solution site. Given so many reduction rules and greedy strategies, 2 questions still remain. The first one is that how to evaluate and apply these reduction rules to maximize the reduction ability. Generally speaking, it is difficult to conclude that reduction R1 is better than reduction R2, even if R2 is dominated by R1, and vice versa. A reduction is more efficient to compute, but may exhibit a limited reduction ability. And the second one is that how to determine the greedy strategy and cooperate with the reduction rules. Now, let me introduce our novel approach, the scheduling framework. Instead of invoking reduction algorithms in a fixed order, we introduce the novel framework which dynamically schedules reduction algorithms based on a cost and benefit model. The scheduler iteratively conducts the following steps until the graph is empty. It first estimates the cost and benefit of each reduction rule, and then choose the best one. If the benefit of the best one is still overwhelmed by the corresponding cost, in another word, the best reduction rule still has a poor performance. Greedy algorithms are invoked to break the tie. So in this approach, the first challenge is how to evaluate and estimate the performance of each reduction algorithm. Facing this challenge, we propose a cost and benefit model to evaluate the performance of each reduction rule. Benefit is defined as reducing ability, which represents the decrease of graph size after applying the reduction rule. Cost denotes time cost. It's simply defined as the processing time consumed by the reduction rule. And finally, the performance of a reduction rule is formulated as benefit density, the ratio of benefit to cost. The second challenge is how to determine which greedy strategy fits the current graph best. Actually, vertex deletion strategy performs better on real networks, and the vertex addition strategy fits ER graphs better. In real networks, there are few high-degree vertices, but a large number of low-degree vertices. In ER graphs, the degree of vertices concentrates around the average degree. Both the numbers of low-degree and high-degree vertices are quite few. In essence, a strategy has a good performance when it gives a good partition. In another word, the gap between the chosen vertices and the others is large. Based on this point, we propose a hybrid strategy. If the average degree is more close to the maximum degree, the scheduler will choose to apply vertex addition strategy to add the lowest degree vertex into the solution set. Otherwise, apply the vertex deletion strategy to discard the highest degree vertex. Finally, let's see some experimental results. Extensive experiments are conducted on 13 real networks and 3 types of synthetic graphs. For ease of presentation, scheduler standard and scheduler extension denote our proposed scheduler-based methods. They are compared with the state-of-the-art algorithms, linear time and near-linear. We also use the exact algorithm VC solver to compute ground truth on some graphs. Figures 4 and 5 present the overall performance of compared algorithms on real networks and synthetic graphs respectively. It is clear that, on large real networks and ER graphs, our scheduler-based methods are much better than the state-of-the-art algorithms in terms of solution quality. As for time efficiency, linear time ranks the fastest since it's really a linear time complexity algorithm. Nevertheless, scheduler standard is at most 2 times slower than linear time. In this experiment, we evaluate how the quality of a near MIS affects a downstream task, K-hop reachability query. An index K-reach is designed to efficiently process K-hop reachability queries, which asks whether there is a path from a node to another within K-hops. The construction of K-reach relies on computing the pairwise distance among nodes in a vertex cover, the complement of an independent set of a graph. Thus, the first step of K-reach is to compute a vertex cover. Here, the K-reach index is constructed based on the near MIS generated by different algorithms onto large real networks. When K equals 4, scheduler extension saves about 10 minutes compared to linear time, but merely uses 1.3 extra seconds to compute the near MIS. These results on the K-hop reachability task demonstrate that it is valuable to further improve the near MIS quality by our proposed methods at the expense of mild extra time cost. In addition to the scheduling framework, we also propose a novel notion representative graph to accelerate the degree 2 reduction, and design a more powerful vertex addition strategy in this paper. Thanks for watching.